So this is the physical science lesson video for section 12.1, and so we're going to start our chapter on forces and motion. And so remember, if you want an easy way to find all my lesson videos in the same place, just subscribe to my channel and you'll have them all there very easily. Alright, so let's get started. So, section 12.1, we're going to talk about forces. So what is a force? A force is a push or pull that acts on an object. So something being pushed or pulled, that is a force. A force can cause a resting object to move or can accelerate a moving object by changing the object's speed or direction. So if something's still, if we apply a force, we can move it by pushing it or pulling it. Or if something's already moving, we can accelerate the object, which means change its speed or change its direction or both. So for example, think about if someone throws a baseball and then another person takes the bat and hits the ball. We have accelerated it because we know we've changed the direction, but most likely when you hit it also you're going to change the speed too, so you cause it to accelerate. So how can we measure force? Well, sometimes we can use a spring scale. So the stretch of the spring in a scale depends on the amount of weight, which is a type of force, acting on it. Okay, so we'll talk about weight here in just a few more slides. So force is measured in newtons, which is represented by a capital N. Okay, so again, I'm really big on correct units, so make sure you remember that. So force is measured in newtons, which is a capital N. So where does newtons come from? Well, 1 Newton is the force that causes a 1 kilogram mass to accelerate at a rate of 1 meter per second squared. So the whole thing is, when you solve a formula for force, you get this big old massive units, kilograms times meters per second squared. And that's a lot to write all the time. So what we do is we just consolidate these units into a Newton. Alright, so that's all a Newton is. This is a kilogram times meters per second squared. And we'll see those units in a few minutes when we do some of the math. So you can use an arrow to represent force. The length of the arrow represents the magnitude and the arrow head represents the direction. That makes it a vector. So force is a vector. Remember, we've talked about vectors a couple of times now with velocity. We talked about vector with acceleration. We talked about vectors. So remember, when we add vectors, we have to use vector addition. So forces, like I just said, combine by vector addition. So if they point in the same direction, we add them together. If they point in opposite directions, they subtract one another. And then of course the net force is going to be in the same direction as the largest number. Okay, so it's overall action on an object after all the forces are combined is your net force. So once you do your vector addition, your net force is what's left over. So for example, here we have 10 newtons to the right and 10 more newtons to the right. So our net force would be 20 newtons to the right because they combine together. Here I have 10 newtons to the right and then 10 newtons to the left. So when I do 10 minus 10, I get 0 newtons. So my net force is there is no force, because those two are pushing in opposite directions. It'd be like if there was a person standing here and I was pushing and another person was pushing, but if we push with the same force, the person in the middle is not going to move anywhere. It isn't until one of us pushes harder that we can have a net force in one direction or the other. So sometimes the net force acting on an object is 0. When the forces on an object are balanced, the net force is 0 and there is no change in the object's motion. Now notice we didn't say necessarily that the object is stopped. There's no change in its motion. So if an object is already moving and 2 balanced forces are applied on either side, those forces kind of cancel out and give 0, it's still going to continue that same motion. But if it's already stopped and we do balanced forces, it will remain stopped. It just means that whatever the object's doing, if you apply balanced forces or opposing forces that cancel out, the object's motion is not going to change. So if it's already moving, it keeps moving. If it's stopped, it stays stopped like that. So an unbalanced force is a force that results when the net force acting on an object is not equal to 0. So in this case, if we have opposite vectors, one of them is a larger magnitude, so we're going to have an overall force. Or if they're both in the same direction, we'll have an overall force. When an unbalanced force acts on an object, the object accelerates. Now remember, acceleration is a change in speed, direction, or both. So remember, it doesn't necessarily mean something's speeding up. You have to take that misconception out of your mind. Okay, so it could mean that it goes faster, it could mean it slows down, it could mean it changes direction, or it could be a combination of those things. So the net force equals the size of the larger force minus the size of the smaller force. Okay, so like if there's 10 in one direction and 5 in the other, we do 10 minus 5, not 5 minus 10, like that. So here's an example of the difference in balanced and unbalanced. So this is tug of war, of course. So here, if you look, our forces are in opposite directions, but they're of equal magnitude. See how the arrows are of the same size? So what that means is that each team is pulling with the same amount of force. So what's going to happen to the flag in the middle? Well, in reality, we know that what it does is it kind of goes back and forth a little bit because we can't, as people, provide perfect, identical forces. But it's just going to kind of hang out here in the middle. Overall, it's not going to really move to one direction or the other. Whereas here we have an unbalanced force. If you look, the red team, their force vector is much larger. That means they're pulling with more force to cancel out the black team pulling. And so what would happen to the flag is it would inevitably go towards the red team because they're pulling with more force. So this would be an example of balanced forces. This would be an example of unbalanced forces. Here's another example. So on our truck, we have 100 newtons of force going in both directions. So the truck was not moving, so since it's a balanced force, the truck stays still. All right, here we have 100 newtons coming from the back and only 60 going towards the front. So overall, that's 40 newtons going towards the front. So that means that since we have an unbalanced force, we're going to cause the truck to accelerate, which in this case means go from stop to moving in this direction. So, what stops things from moving? Well, all moving objects are subject to friction, a force that opposes the motion of objects that touch as they move past each other. Okay, so when we're trying to move something, what we're usually having to work against is friction. So there are 4 main types of friction. There's static friction, sliding friction, rolling friction, and fluid friction. So let's talk about what each of those are. So static friction is the friction force that acts on objects that are not moving. Static friction always acts in the direction opposite to that of the applied force. So here we have this little boy and he's trying to push this gigantic rock. Is that rock going to move anywhere? No. But is he working hard applying a force on that rock? Yes. He's pushing with all his might, even though the rock's not going to move. Because why doesn't the rock move? With the friction. The rock is not going to move because of the friction between this rock and this rock. So the boy is pushing in this direction. So that means static friction is working in the opposite direction. And the friction is so much that it's causing the objects to not move. Okay, that's what static friction is. Sliding friction, on the other hand, is a force that opposes the direction of motion of an object as it slides over a surface. So see, in the previous example, the boy couldn't get the rock moving, so he didn't experience sliding friction. He was experiencing static friction because he never could move the rock. Whereas here, this is a football player at practice, and he's pushing this across the grass, and so it's sliding across the grass. Why is it difficult to slide it? Well, because of friction. If there is no friction, you could just push that thing with your hand, and it wouldn't even be a big deal. All right, so he's pushing, or these 2 guys, they're pushing in this direction to the right, so that means the sliding friction is in the opposite direction to the left. It does not want this to move, whereas the 2 guys, they want to push it so they can get done with practice. Rolling friction. When a round object rolls across a floor, the object and the floor are bent slightly. So that's the thing, is when 2 things are rolling past one another, there's a slight bending at the atomic level. The change in shape when something rolls is the cause of rolling friction, which is the friction force acting on rolling objects. All right, so even when you're rolling something, there is a little bit of friction, because if I push something on wheels, is it eventually going to stop? Yes, that's because of the friction. If there was no friction, if I pushed something on wheels, it would just go on forever. Okay, so there's obviously friction even acting on rolling objects, and that's because of that slight bent out of shape that happens as something's rolling. Like, think about a tire. If it's not very well inflated, you can actually see how the bottom looks a little flatter as that tire's rolling around. So just know that even with harder objects, it happens at the atomic level. You probably can't see it. And then fluid friction. First of all, we need to make sure you know what a fluid is. So fluid is a substance that flows. Everyone knows that liquids are fluids, but gases are also fluids. Okay, a gas can also flow. So the force of fluid friction opposes the motion of an object through a fluid. So again, it's the same thing with all friction. It's always in the opposite direction of the motion. So if I'm trying to go this way, friction's trying to go this way. It doesn't matter if it's static, sliding, rolling, or fluid. So fluid friction acting on an object moving through air is also known as air resistance. Okay, so think about it this way. When you're swimming, you're having to force yourself through that fluid because you're trying to go one way, that fluid friction is going the other way. Same thing when you jump out of an airplane. Okay, you're trying to go down towards Earth because what's pulling you down? Gravity. But why is your hair and why is your face flapping? That's friction of all that air passing you, trying to go in the upward direction. All right, so just remember, friction's always in the opposite direction of motion. So now let's talk a little bit more about that gravity, now that we saw that skydiving. So gravity is an attractive force that acts between any two masses. So like right now, even me and this marker are experiencing gravity. So you may think, okay, well, why isn't the marker like coming to my body? All right, well, not all gravity is strong enough to pull two objects together. Like if I jump, Earth's gravity is strong enough to pull me back down. But this marker and I, we're too small to have a big enough gravitational force to where this marker feels the need to fall towards my body. Gravity does not require objects to be in contact for it to act on them. All right, so a lot of the force we've been talking about is we're touching, like we're pushing something, we're pulling something, we're rolling something. Well, gravity happens even if we're not in contact. So if I fly all the way up in an airplane and I'm not even in contact with the Earth, if I jump out, the Earth is still going to pull me back. Okay, so gravity can act over large distances. So let's talk about those falling objects like that man skydiving. As objects fall to the ground, they accelerate and gain speed. So like when you're in the airplane, you first jump out, it's not super scary, and then you go faster, 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 faster until you hit the ground. Well, I mean, obviously hopefully you'll pull the parachute. Never mind, don't fall until you hit the ground. Hopefully you'll pull the parachute and then you'll slow down and hit the ground. All right, so you accelerate and gain speed. Gravity causes objects to accelerate downward towards the Earth, whereas air resistance, that's our fluid friction, is acting in the opposite direction and it's trying to reduce your acceleration. So as you're falling, gravity is like pulling you down, but air resistance is trying to keep you up. It wants to slow you down because you're having to pass through, like all those air molecules have to get out of the way. That's sliding past you, that's causing all that friction. So as the speed of a falling object increases, so does the air resistance. So the faster you start falling, the more you're going to feel that air resistance. That's why people's cheeks will start flapping and things like that when you're falling very quickly. Now, can you fall faster and faster and faster forever? No, and it's not just because you'll hit the ground. There is something called terminal velocity, and that is the constant velocity of a falling object when the force of air resistance equals the force of gravity. So remember, gravity is trying to pull you down. Air resistance is trying to push you back up. So once those two become equal, you'll fall at a consistent speed. Remember, we said if an object is already moving and balanced forces are placed on it, it just continues with that same speed. Okay? So once those two become equal, that's when you fall at what we call terminal velocity. You're going as fast as you can. Unless something was to propel you at that point, you would not go any faster. So next thing is projectile motion. So projectile motion, think about if you have like a marble on the table and you just kind of like flick it off the edge. Okay, and so it's going to kind of project down onto the ground. So projectile motion is the curved path of a falling object after it is given an initial forward velocity. So if I come over here and here's my marble and I thump it, depending on how hard I thump it will depend on which path it takes. But notice all three of the paths are curved. So the combination of an initial forward velocity and the downward vertical force of gravity causes the ball to follow the curved path. So I'm trying to flick it this way, but once the table is not there to support it, what has a hold of it now? Gravity. So it's still trying to go in this direction, but gravity is just pulling it lower and lower and lower. So that's how you get that curved path. All right, and so that's an example of projectile motion. So an object that is dropped and an object that is projected will strike the ground at the same time. Now this is something that's hard for people to understand because you feel like the projected one should take longer to hit. It's just going to hit in a different place. So if we have two marbles and one I'm holding at the level of the table and one I thump off the level and I do them at the same time. So I thump and drop at the same time. The one I drop, it will fall straight down and hit. Let's say it takes 1.5 seconds. Alright, so it falls in 1.5 seconds. The one I project will also hit at 1.5 seconds, but it's just going to be across the room a little bit. Okay, they have a good Mythbusters video on this where they tested it, but they used a gun and they tried dropping a bullet and shooting a bullet at the same time, and you know how Mythbusters work. They decided if it was busted or not. So, you know, check that out so that way you can see in real life this happening. Alright, so let's knock out this section assessment. So how is the motion of an object affected when a force acts on it? Remember, when a force acts on it, it could be balanced or unbalanced. So remember, a force is a push or pull. So what we could say for this is a balanced force will not change the object's motion. An unbalanced force will change an object's motion. Okay, so for the first one, I would say a balanced force will not change an object's motion. An unbalanced force will change an object's motion. Because the motion of an object is actually not affected if the force is balanced. Alright, list the 4 types of friction. Well, we just listed them. So we have static friction, sliding friction, rolling friction, and fluid friction. Alright, so static friction, sliding friction, rolling friction, and fluid friction. So how does air resistance affect the acceleration of a falling object? Remember, a falling object is falling due to the pull of gravity towards the earth. But what direction is the resistance in? So gravity is pulling down, so air resistance is pulling up. So what does it try to do? It tries to slow the object down. So if it says, how does air resistance affect the acceleration of an object? It tries to slow the speed or decelerate it. Alright, so it tries to slow the object down. So number 4, Earth's gravitational force acts in what direction? You know this? Acts downward towards the earth. Alright, compare the strengths of static, sliding, and rolling friction. All you have to do is think about it. Think about if you're moving a huge box. And it is a box that contains a refrigerator. And you're just a little kid. Let's just make it, because I know some of you out there are stronger than me and could probably push a refrigerator in a box. Okay, say you're a little kid and you're trying to push a big box with a refrigerator in it. And so you push, and that refrigerator doesn't move. That's static friction. If you can't even move it, static friction must be really strong. Whereas, let's say on the other hand, it's a box, and it's really big and heavy, so you can't lift it up, but you can at least push it and slide it across the floor. So you're pushing and sliding. Obviously, it's less friction than static because you're actually able to move it, but you're still getting a lot of friction. What if you were to take that box and put it on a cart that had wheels and you could just roll it? Is it going to be a lot easier? Yes. That's because rolling friction is less. So for this one, static is the strongest, sliding is in the middle, and rolling friction is the lowest of those 3. Okay, like I said, you can't even move this one. Sliding stuff sometimes is pretty difficult, but rolling is the easiest. So number 6. Explain why falling leaves often do not fall in a straight line path. So think about a leaf falling. It doesn't just fall like this. It's like doo, 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 doo. Okay, what's causing that is that fluid friction or air resistance. You can put either for that one. Fluid friction or air resistance is causing it to sit there and do that back and forth motion. Because remember, the air resistance is trying to keep it up, but gravity is pulling it down. Alright, and then number 7, it says 2 coins are knocked off of a table at the same time by different forces. Which coin will hit the floor first? Well, remember, when we're talking about projectile motion, it doesn't matter with what force it's pushed off. That just determines where is it going to land. But the fact that they're both released from the same height means they're going to hit the ground at the same time. Okay, again, if you're still questioning that, just watch that Mythbusters video about the bullet. Alright, so that is section 12.1, so hopefully now you understand about friction and forces.